Good morning, learners. My name is Ada Maina. I'm going to take you through physical electronics topic on full wave rectifiers. Subtopic: center tap full wave rectifiers. The objective of class the objective of the class today will be, by the end of the lesson, the learner should be able to define a center tap full wave rectifier, identify the component of a center tap full wave rectifier, explain how a center tap full wave rectifiers work both during the both half cycles. So a center tap full wave rectifier is defined as a circuit that uses a center tapped transformer and two diodes to convert both half of the AC input into pulsating DC output. So the keywords in this definition are: it is a circuit. Note it is a circuit. It is a circuit that uses center tapped transformer and two diodes. It uses two diodes to convert both half of the AC input into pulsating DC output. Note this word, pulsating DC output. This is a keyword and it has a lot of meaning. So in the right hand side, we can see the schematic diagram of a center tap full of rectifiers with two diodes, D1 and D2. D1 will be forward biased during the positive half cycle, and D2 will be reverse biased during the positive half cycle. But during the negative half cycle, D2 will be forward biased and D1 will be reverse biased. So you can see the diagram of it. Here we have the primary windings, which are the AC input, and the secondary windings. Component of a center tap full wave rectifiers are diodes, which are two diodes, one for positive half cycle and the other one for negative half cycle. A center tap transformer, we can see the 3D view of it. This is the 3D view, and a 2D view. 2D view. We have a resistor, which is the output. We have both the 3D view and the 2D view of it. The working principle of a center tap full wave rectifiers, as it is illustrated. Each diode conducts during alternate half cycle of the AC input. Diode 1 conducts during the positive half cycle and diode 2 conducts during the negative half cycle. This allows current to flow through the load in the same direction during both half cycles, producing a full wave rectified output. Note that during the positive half cycle, point A in the diagram will be positive and point B will be negative. So at positive half cycle, diode 1 will be forward biased and current will flow through it. But diode 2 will be reverse biased as there will be no current through the diode 2. During the positive half cycle, the current will flow in this direction, in this clockwise direction. And during the negative half cycle, point B will be positive and A will be negative. So diode 2 in the negative half cycle will be forward biased and diode 1 will be reverse biased. So, but regardless of the positive half cycle or negative half cycle, the output and the DC output will be the same. You can see it will be still anti-clockwise, but the same direction of the output. So we have the AC input, our graph, the positive half cycle and the negative half cycle will be the lower negative side of the graph. The DC output, which is illustrated shown here. Yes. So in our next video, we will have a video together with a diagram. So I'm going to play the video and you will see how the current will flow through the diode during the positive half cycle and during the negative half cycle. So you can see during the positive half cycle, diode 1 is forward biased and the current will flow in it in clockwise direction, and the output through the road, which will be the resistor. So during the negative half cycle, you note that diode D2 will be forward biased and diode 1 will be reverse biased. But regardless of either positive or negative half cycle, the output at the DC, how current will flow at the DC load, is the same. That's why it is a full wave rectifier. So we have, you can see we have the 40 hertz input, and below there we have the graph of the output. This is the graph that indicates how the output is, which is the DC, which is the pulsating DC output. So the advantages of a center tap full wave rectifier are higher efficiency, lower LiPo factor, better transformer utilization. So we have the high efficiency, it has high efficiency trap full wave rectifier, lower LiPo factor, better transformer utilization. Note this word. So a full wave rectifier, we can summarize with a half wave rectifier. It has advantages. In average output voltage, this part, we can see that a half wave rectifier is lower, but for a center tap full wave rectifier, it is higher. In a LiPo frequency, same as the AC, double the AC, its advantages. Transformer utilization, it is poor, but this is better. The efficiency is low, and it is better efficiency. So we can have a recap of what we have gone through today. We have defined the center tap full wave rectifier. We have gone through the components, and then we have concluded by the working principle of a center tap full wave rectifiers. That is the end of our lesson today, and thank you for your time. Have a nice day and take care.